Okay, so get this. Imagine something 1,000 times smaller than a grain of sand just kind of floating in midair, held there by, get this, light.
Light.
Light. That's what these researchers at ETH Zurich, I think it is.
ETH Zurich, yeah.
They figured out how to levitate these nanoparticles. It's wild.
Yeah, no, it's incredible. It's not sci-fi, though. This is like real physics.
Hardcore physics happening right now, and we're diving into it all today. We've got the paper from Nature Nanotechnology, and let me tell you, they did not skimp on the visuals and data this time.
There's a lot to unpack.
A lot. We're going to be throwing around terms like optical trapping, cold damping.
Phonons,
all that good stuff.
It sounds intimidating, but honestly, when you break it down, it's fascinating. Think of optical trapping. Like, imagine using light, but like a tiny invisible tractor beam to hold something so small you couldn't even see it.
A microscopic tractor beam.
Exactly.
I love it. Okay, so they're trapping these nanoparticles. What's the setup look like?
So picture this. A miniature stage, like unbelievably small, obviously. That's our chip.
Okay.
And the chip's got two main parts. You've got your photonic layer, and then there's the electric layer.
So the photonic layer, that's our tractor beam, right? The spotlight that holds the nanoparticle.
You got it. That's the optical trapping in action.
Yeah.
But the really clever bit, that's the electric layer. That's like our behind-the-scenes crew.
Keeping everything running smoothly.
Exactly. See, at this scale, everything's always vibrating. It's just like constant jitters. And that makes studying anything precisely a nightmare. So the electric layer, it acts like a super-powered cooling system. Brings the nanoparticles' energy way, way down. We're talking near absolute zero.
Near absolute zero. Isn't that, like, impossibly cold?
It's insanely cold.
Yeah.
But that's how they manage the cold damping. They essentially freeze those vibrations in place.
Wow. So it's like, I don't even know, trying to study a hummingbird's wings while it's, humming, everything's just a blur.
Exactly. But if you could somehow get that hummingbird to just hover perfectly still.
You could see all the details.
Exactly.
Incredible. Okay, so we've got our microscopic stage, our spotlights on our nanoparticle, and we've got the crew keeping things cool and calm. What happens next in our nano-sized performance? So what happens next? It's like we've prepped this whole stage. What's the main act?
So remember those phonons we talked about earlier? Those vibrations inside the nanoparticle?
Yeah, the ones we're trying to, like, totally freeze with the cold damping.
Right, right.
All right.
So it turns out we can actually use those phonons. Like, we can use them to learn even more about the nanoparticle itself.
Hold on. How do you use something you're trying to get rid of?
Okay, think of it like this. You know how when you, say, strike a bell?
Makes a sound.
It vibrates. At a specific frequency, right? Creates that tone.
Okay, yeah.
Now, imagine you could reach in and, like, just barely, just so slightly, change the shape of that bell.
The sound would change.
Exactly. That tone would be different. And that's kind of what they're doing here. But instead of a bell, it's our nanoparticle. And instead of touching it, they're using light.
They're using light to ring this nanoparticle.
I mean,
It's wild, right?
that's amazing. But, okay, how does that actually help them study it?
So by adjusting, like fine-tuning, the light they shine on it, they can control those vibrations really precisely. Make it vibrate faster, slower, even in specific patterns.
So they're basically playing this nanoparticle like a microscopic instrument. But it's not just for the music, right? What's the point of all this?
No, there's a bigger picture here. So by studying how those vibrations change how the nanoparticle reacts to the different light, they can figure out some of its basic properties, like its mass, its shape, even its internal structure.
Wait, so it's like using sound to see?
Kind of. It's more like using one type of energy, the light, to manipulate another, the vibrations, and then from that, they can understand what's happening at this crazy small scale.
That is incredible. It's like we're watching the quantum world, like, actually happening.
Yeah, and it's important to remember this is like a whole new level of control, a level of sensitivity that opens up so many possibilities. Okay, like what could you actually do with this? Okay, so we're talking about controlling these tiny vibrations, but what's the payoff? What does that actually let us do?
Well, imagine, like, being able to actually feel the weight of something 1,000 times smaller than a grain of sand.
We're talking some seriously sensitive scales.
That's right. We can measure forces now that we, like, couldn't even dream of before.
Yeah.
This level of precision, it's insane. And remember how we were talking about cooling that nanoparticle down near absolute zero?
Yeah, the whole cold damping thing. Wild stuff.
So it turns out, down at those temperatures, materials, they start doing some pretty freaky stuff.
Freaky how?
Think quantum behaviors. That's where things get really bizarre.
Okay, yeah, quantum stuff, always a wild ride.
And the exciting part is, this tech, It lets us study that craziness up close, not just on the level of like single atoms, but on a bigger scale.
So we're bridging that gap between like the quantum world and, our everyday reality.
Exactly. And that's where it gets really mind-bending, honestly. The paper even talks about creating macroscopic quantum states.
Oh, and macroscopic quantum states, break that down for me.
Okay, so imagine a single atom, and that atom exists in two places at once. That's like classic quantum weirdness. Superposition, they call it.
Yeah, the whole is the cat alive or dead thing, right?
Exactly.
Yeah.
But now, picture that, but scaled up to
Uh,
something you could actually see. That's a macroscopic quantum state. Taking that quantum weirdness and bringing it into, like, our world.
wow. Okay, my brain is definitely doing backflips trying to picture that. So this is like way bigger than just levitating nanoparticles
Oh,
now.
absolutely. We're talking about changing how we understand the universe.
Exactly. And to think, we started with just some tiny tweezers made of light.
It shows you the power of just, like, pure scientific curiosity. We poke at the unknown, and who knows what we might find. And the applications for this, sky's the limit. Quantum computing, crazy sensitive sensors, new types of medical imaging, you name it.
So, to everyone listening, next time you see a speck of dust floating, just remember it might be a gateway to another dimension. Or maybe it's a tiny dancer in a laser show, but maybe, just maybe, it's a glimpse into the future of technology. And that's it for today's deep dive. We'll catch you next time for another adventure into the world of cutting edge research.